Swayam Prabha. Digital India. Educated India.
There is another example that we will discuss where the hydroxy group adjacent to a leaving group, but the hydroxy group is a tertiary hydroxy, and if that is adjacent to a leaving group on adjacent carbon, then you will have scenarios where ring contraction can happen or ring expansion can happen. Okay. So, here is an example. I just put a general scheme first and then we go on to specific. In both the cases, we are treating with base, right? So, what will happen first? It will obstruct the proton, form O minus, right? So, the intermediate will have now moment you have generated the O minus, oxygen will have 3 lone pairs. What should happen? It will push this carbon-carbon bond it should push the carbon-carbon bond, it will migrate to the adjacent carbon-carbon bond, displaces the leaving group, right? So, what will be the net result? Ring expansion or contraction? Ring contraction. In the second case, similar scenario happens. O minus ring expansion. So, what is the structure you would get? Ring expanded structures. Okay. In both the cases, if you look at carefully, there are 2 events that have happened. Both are of SN2 type, right? What is the first event? Oxygen lone pair falling back, pushing this CC bond. Once this CC bond migrates, leaving group has to leave, right? So when the leaving group has to leave, then it has to, the migrating group should come behind the leaving group, right? Attack should happen from the back side, and a collinear arrangement is necessary for that to happen. Only then the leaving group will be lost. So it is of SN2 type. Now let's take a specific example. So electron pair displaces the CC bond, and if electron pair has to displace the CC bond, what is the requirement? It should be anti-periplanar to the CC bond, and that pushes CC bond migrates, right, with the assistance of the lone pair, and now CC bond migrates, it approaches the back side, and then it makes the CX to leave, to cleave and leave as a leaving group, right. So this kind of a situation you must have studied in many of the reactions, but we will not realize the involvement of the lone pair in the reaction, but you will just use it by arrow. Many of you must have used it by just pushing the lone pairs, putting an arrow, and right. But which lone pair, which bond, which is the orientation? What is the orientation that is necessary for the lone pairs to make this happen is something that is very, very crucial. If it is not an anti-periplanar orientation, then it is, that particular group is not going to migrate. Okay, the necessity is the orientation of the group. Okay, let's take one example. That is the leaving group. Right. So O, it is already deprotonated. Now if we have to draw in terms of orbitals, it is better for you so that it is now the question is, which is the substituent that would migrate from here? So O is there, right? It has a negative charge. What is the group that is going to migrate in this, from this carbon, R1 or R2? R1. Do you see an anti-periplanar geometry for R1? What is the lone pair that is, or what is the electron pair that is anti-periplanar? This particular one. This is anti-periplanar. So what does it do? It should share the electron density to sigma star of R, CR, right? So this CC bond, it comes in, weakens this CC. So obviously it should migrate. When it migrates to the adjacent carbon carrying the leaving group, the orientation should be in such a way that it makes a collinearity with the leaving group. So when it migrates like this, right? So that there is a collinearity achieved, and hence the leaving group could depart. right? So this is the group that is now migrating to this carbon, and then you see that this X is. Now there are three conditions, two conditions you are carefully paying attention to. One is this oxygen lone pair being, or the electron pair being anti-periplanar to the CR bond, and this CR bond being anti-periplanar to the CX bond. Okay, so this arrangement is very, very, very crucial for a migration to happen. So assistance is happening through the electron pairs, and then this R1 migrates to leave the leaving group. What is the net product? R2 is here, double bond O, and then you have R1, R1 this side, H should be here, and then R2. Okay, let's just reverse the situation and then try to understand. So you have a scenario like this, let us say. R2, R1 is at the front, and then you have oxygen. So you have the lone pair, 1, here you have R3, X, H. Just reversing the scenario. Now, which is the migrating group? So, what you have to pay attention is the leaving group and the migrating group should be anti-periplanar. And if this group has to migrate, there must be a lone pair which should assist, right? Which should be available again in anti-periplanar fashion. What is the lone pair among the three that is anti-periplanar to R1? It is this one, right? So this lone pair is anti-periplanar to this R1, and now this R1 is anti-periplanar to this CX, right? So this assists in pushing the N to NO to C sigma star. Then this migrates, right? Collinear attack. The leaving group is good. So now again R1 comes here, H is there, R3 is there. Okay, so this should be some mistake. This should be R3. Is it clear now? So you need the assistance of the oxygen electron pairs. Only when it comes, because it's not like that, it keeps rotating, right? So when it is happening, and when a particular electron pair comes anti-periplanar to this R, that assists at that moment for the R to migrate, to the adjacent carbon. And why this R does not migrate? This R is not anti-periplanar to the leaving group, right? So when you also need the assistance of the low electron pair of the oxygen, and that should contribute to the migration. Okay, now let us keep the O anti-periplanar to X. Then what will be the result? If O is anti-periplanar to the X, we draw the structure. There is a space, okay. R2, R1 is behind because we want to keep O anti-periplanar to the leaving group. R3, X. If we keep this O anti-periplanar to the then what can happen? Oops, sorry. Here. We are done with this. So if oxygen is anti-periplanar to the leaving group, O minus is anti-periplanar to the leaving group, what will you see? O is anti-periplanar to the CX. What can happen is this lone pair is O minus. What do you get then? No, you would get an epoxide. Under what conditions you get an epoxide? Under what conditions it starts to migrate, right? So conditions when the O is O minus is anti-periplanar to the leaving group, then you get an epoxide. Because epoxide transition state, if you see, epoxide ring opening will have, this is a epoxide, let's say you have you want to ring open this epoxide using a nucleophile. Let's say Y minus is again the nucleophile. So the approach should be like this. Collinearity, backside attack, all that is what you will implement. So Y minus is the nucleophile, you want to open this epoxide. Under that conditions, you will see a transition state which is slightly longer than this. So you will see a transition state where it's not symmetrical from either side. This is longer and this is shorter. What you will see here is initially longer. When it starts to form the bond, then this gets weakened, it departs, and then you get a symmetrical system. Okay? So this leads to an epoxide formation. Right? So the arrangement of the leaving group, incoming nucleophile is important. In our case, we saw the incoming group is the migrating group. We also saw the internal nucleophile that, intramolecularly attacks the carbon carrying a leaving group and then displaces it to form the epoxide. Okay, so stereoelectronics in all these cases play a very, very crucial role that you must understand. And let me go to another example where a similar scenario is discussed as well. You must have studied pinacol-pinacolone rearrangement. Now you apply this understanding there to try to identify why a particular group undergoes migration over the other. There the leaving group is the protonated form, correct? Protonated OH. So pinacol, you treat it with the acid, one of the hydroxys get protonated and that becomes the leaving group, and then one of the alkyls migrate with the assistance of the electron pairs from the OH, right? Now the assistance of the electron pair, you will know why certain group migrates and not the other group on the other side. Only one particular group migrates and leaving group should be anti-periplanar to the migrating ones. Those are only successful. The other ones which are not in a proper orientation will not take over, particularly in a locked systems where there is no free rotations, right? So the migration of the bond, particularly conformationally rigid systems, let us say, flexible or this kind of acyclic systems are fine. But if you are looking for a cyclic system where conformational freedom is little restricted, so the group that is, if it is only anti-periplanar, that will undergo the migration, otherwise it is not. Okay. So keep that in mind when you are working out the mechanisms for certain things. Yeah, here is another example where the migrating bond is again anti-periplanar. Amino alcohols, vicinal amino alcohols. Okay. So if you treat this with nitrous acid, this example you must have studied, I suppose. So have you studied this example? No. This forms a diazonium. Right? Where is the leaving group here? Diazonium. Right? So you have formed the diazonium, the treatment with nitrous acid. So now you need to identify the anti-periplanar unit to the leaving group. Right? What is the bond that is anti-periplanar to the leaving group? What is the bond that is anti-periplanar to the leaving group? Are you able to locate this? Right? Now, what is the role of oxygen? Need to draw another lone pair. Okay. So now you also see a lone pair that is anti-periplanar to this. Now this lone pair is going to pump in the electron density to the sigma star of Cc, and then this Cc bond migrates to the adjacent carbon carrying the leaving group, right? So this unit migrates, comes here and then leaves this, displaces this particular unit, leaving you a ring contracted cyclopentane carbaldehyde derivative. A similar compound could be obtained from a different starting material, which is when the amino group is equatorial and hydroxy group is axial. So treatment with nitrous acid again converts this amino to now where is the migrating group and where is the leaving group? Migrating group and the leaving group are anti-periplanar to each other, right? So leaving group is N2 plus here. Okay, what is the bond that is anti-periplanar to this? It is this. There is also this bond, but it doesn't have an assistance of the OH. Please keep in mind, you will see when things are connected, you may locate another anti-periplanar bond, but that anti-periplanar bond does not have a benefit from oxygen, okay. So this particular bond is anti-periplanar. Now again you need to see if there is an assistance from the lone pair of oxygen. You will indeed have, because this group can rotate, what you will have is here right. Now this particular electron pair is anti-periplanar to this. So this will pump in the electron density here. This group will migrate, okay, and then this would leave. What will be the product again? Again you will get the carbonyl, because of this interaction, the single bond now becomes a double bond, and that's what was seen in the product. And then migration happens, you will see a ring contraction resulting in the same compound. Okay. So what is very much necessary is the help of this particular group, okay, to initiate this migration and then displace the leaving group. So it is very, very important. Okay, what happens in a situation when the alcohol is equatorial? And amino is axial. First step is quite straightforward. Now what is the next step? You have to locate the antiperiplanar group. What is the antiperiplanar group here to the leaving group? To this bond, what is the antiperiplanar bond? This is axial. The CH is in axial position. So there should be some other substituent in axial. Only then it will be antiperiplanar. So if this is axial, this is the group that is axial. This carries the OH. You can also think of another axial bond which is this, but that doesn't have OH. There is no assistance from oxygen. So you need not worry about this, but what you should worry about this OH, because that is attached to oxygen. Now you take the influence of the lone pair, which can be right. This is antiperiplanar to this H. Now you don't need to memorize any mechanisms, but if you are familiar with these kind of migrations, movements based on the assistance from electron pair, then I think it is very much simplified. And what you will have in this situation is what? You will get a cyclopentanone. Why? There is no ring contraction. There is no alkyl group undergoing migration. It is just a hydride shift, right, which has happened from here to the adjacent one. So it just walks on the backbone, then pushes it. So what you have is the net result is tertiary-butyl cyclohexanone. Okay, one more example and then we stop. Whatever we have done previously, we are now trying to put it on a cyclic system and then understand it. OH, both the groups are now axial. Nitrous acid, again you convert that to a good leaving group. Let's put the hydrogens also so that we can understand what is happening. Okay, now what is the next step? You need to identify the antiperiplanar group. Do you have anything? Yeah, you have something. Here is a H. This H is antiperiplanar to this leaving group. There is also this OH that is antiperiplanar to the leaving group. Right? This H can it migrate? It cannot, because there is no assistance from oxygen. Now, if you take this hydroxy, what would it do? It is antiperiplanar to the leaving group like we saw before. So what does it do? It should form an epoxide. So that's what is actually happening. The lone pairs of this would assist in displacing the N2, right? And what you ultimately form is an epoxide. you will get an epoxy. Right. So the various arrangement of the substituents and the leaving group, right? You can visualize it based on the arrangement of lone pairs, arrangement of the migrating tendency of these group, how they migrate, and then the leaving group leaves. So you should be able to. You can also do the same exercise, just don't keep the tertiary butyl. When you keep tertiary butyl, it is locked, right? Equatorial substituents are in equatorial and axial substituents are in axial. But moment you remove this tertiary butyl, now the cyclohexane ring could be flexible. So they would undergo rapid conformational motions. And now the axial substituents could go to equatorial. Equatorial substituents can become axial. Then the complication is too much. Then you just think of writing different structures, different conformations, and then see what could be the products. Because if both the conformations could be achieved and both the conformations should lead to different products, or it can lead to the same products as well. But you need to find out by drawing the right conformation, just see, because there is an equilibrium between the two conformers, and you can elucidate the products result, net products results as well. Okay. So that exercise you may try. So get a cis epoxide at the end. Okay, benzylic acid rearrangement you must have studied. It happens under what condition? It is in basic condition, right? So you have a benzyl to start with. Benzyl to start with, and then you have OH minus, let us say, it's a base. Now you get a tetrahedral intermediate, OH, finally the AR migrates, right, to give you a carboxylic acid. So you have O minus AR right. This intermediate is very crucial. The intermediate that you have generated here is very crucial because AR migrates to the neighboring carbonyl. Correct? And how does that happen? Again, there must be assistance from oxygen lone pairs, right? So if you want to draw that, we take this structure AR C O Can you now locate this? This oxygen has a negative charge, this also has a negative, that's why we wrote 3 lone pairs. Now, this lone pair is antiperiplanar to, oh sorry, not this one, this one. The one here. Right? This particular lone pair is in antiperiplanar geometry to this AR bond. So this, this, right? So how many of the secondary electronic effects are there? 2. So this is right. 2 of these electronic effects are causing this AR to shift. Okay. So then this AR migrates, and then you have this is O minus, right? So this, when this migrates, this becomes O minus. So to start with, it is CO. To start with, it is CO. So you need to have this primary electronic effect, plus you also have that lone pairs of the oxygen. So now this migrates to this, right, to the pi, and then this lone pair migrates. What you see is breaking the primary electronic effect, you create a aryl migration, and hence finally this product is generated. So in every rearrangement, whenever you see a migration, even it could be a carbocation based rearrangement, right, you will see the electrons, how they are influencing, what is the role of this electron pairs. It could be bonded pairs in the case when you see the migration. Whenever you saw oxygen or nitrogen or sulfur, again the lone pairs of them or the electron pairs sitting on the heteroatoms could assist a particular phenomenon in the reaction, such as bond migration and so on. Okay. So this is the assistance that you get in every reaction. Similarly for Favorsky rearrangement also, right? In Favorsky rearrangement, when the bond migrates to form a ring contraction, right, then also you will see the lone pairs assistance for this particular bond to migrate, and many such examples are available. It is just that you must have to pay some attention to those details. Methyl and neomethyl chloride, have you looked at the elimination possibilities? You have studied their elimination possibilities? No. Beckmann rearrangement, what is that about? Beckmann rearrangement is what? From the oxime to amide, right? Again there you saw a migration, phenyl undergoing migration, right, to the adjacent nitrogen. So this again is driven by the electronic effects that we saw, right? Anyway, so I will just talk about the neomethyl chloride, and we are close to the time, I think. This is neomethyl chloride. Another one is methyl chloride. Just the difference in their stereochemistry. This particular isomer presence of base gives a mixture of two products after elimination. In a ratio of 1:3. Right, in a ratio of 1:3. This compound, this is a methyl chloride, sorry. When you treat it with sodium methoxide, gives you only one product. It gives only one product. You can now, just by looking at the structure, you will say that this formed a less substituted olefin, correct? This formed a more substituted olefin following, what is that rule? Zaitsev rule, right? So this follows the Zaitsev rule. So what is the reason? How do you explain this? What? Can draw structures of these two? Let's draw a structure of the starting material. So if you have to draw for the neomethyl chloride, so these two are cis. So if you place this equatorial, other one should be in axial, and that is, so this should be trans, that's the methyl. Now you place the hydrogens appropriately. Right? This is one conformation. Let's look at this conformation. The leaving group is Cl, right? So if it has to happen, yeah, so you need to look at the antiperiplanar hydrogens. How many hydrogens are present? For this Cl to leave, these are the two hydrogens that are antiperiplanar, right? So that explains the possibility of two products. But we also look at other conformation of this, we cannot rule out, right? So we will write the equilibrium, we will write the next conformer of this. Where this is axial, that chlorine becomes now equatorial, H is axial, here again H axial, where is that methyl? Methyl should be this. In this case, what do you see? No, but you need to identify the hydrogens that are antiperiplanar to this. How many of them are there? What is that? No, axial is antiperiplanar to axial. What is the one? Equatorial hydrogen. So equatorial hydrogen is here, right? Equatorial hydrogen is here. So either cases, what you will see is two product possibility. If you take this particular structure, but this is possible or not, this conformation to achieve? Possible? Why possible or why it's not possible? You have this such a bulky group isopropyl at the axial. You will have severe 1,3 diaxial interactions. These hydrogens would now, impose a huge steric environment. Now you should know, you should use the term steric, right? Because how many distance? 1, 2, 3, 4, 5 and more than that. More the bonds greater than 4, you are just hitting the hydrogen because that bond comes into the hydrogen. Then rotation becomes really difficult for that group and hence this is a steric. So this is not a favorable conformation. It would immediately come back to this. And when it comes to this conformation, you have possible 2 hydrogens. So you get a more substituted product, olefin, as well as a less substituted olefin. When you are talking about this particular compound, so this is trans, right? So if this is equatorial, and this should also be equatorial, you have hydrogens here, you have hydrogens here. Now you identify what is the antiperiplanar hydrogen for this. This is a leaving group, right? What is that one? It is the one on the equatorial on the other side. Right? You can have only one product possibility. You understand? Yeah, so we stop here. So we have few more examples, but you can apply them. You can apply them and then find out how you can rationalize the reactivity based on the conformation. Okay, thank you.
Swayam Prabha, Digital India, Educated India.